Welcome to the lecture. We are now going to make a comparative discussion of covariance versus invariance principle under general coordinate transform. So from our previous studies, we have seen that the gauge symmetry of the gravitation is nothing but a general coordinate invariance. So if we level all the spaced points x to some x prime, I'm not writing the for index explicitly, and this x prime, some arbitrary function of x, arbitrary function. And this is called a general coordinate transform or GCT. Now we have seen that whenever we want to couple any matter field, be it a point particle or it can be other fields like electromagnetic field with the gravitation. So this coupling has to be consistent with this gauge symmetry or this invariance under the general coordinate transform. Okay. In fact, the dynamical equation governing any physical system interacting via gravitational field or the equation of motion of the gravitational field itself should be invariant under the general coordinate transform. But this is not same as demanding that equation is covariant under G. So let's make this very clear, because this will help us to clarify certain important conceptual issues and will be very important when we embark on a journey to understand or develop the formalism to study the full nonlinear theory of gravity, where the dynamical equation will be governed by Einstein field. So if both sides of an equation transforms identically under this GCD, that is, both sides of equations are tensors of the same type, then the equation is guaranteed to be covariant under general coordinate transform. So by covariant, it means it's a form invariant. Covariant, right? Form invariant. That is, equation will look same no matter which coordinate systems you go to. You can arbitrarily level the space-time points, but the form of the equation will be identical. So for example, let's consider the equation of the form mu. This is left hand of this equation, the tensor of rank 2, 1. The other hand, right hand side, will have, let's say, product of tensor the following way. And these indices are contracted, both left hand side and right hand side, only 3 free indices, and 2 is up and 1 is down. So both left hand side and right hand side, you can check that behaves as a 2, 1 rank tensor under this GCD. Right? So under the, it will look like, if we go to some prime frame, again look the same. So A, B, C, D, they will go to some A prime, B prime, C prime, but the form of the equation will remain the same. And that is guaranteed because both sides is a 2, 1 rank tensor. On the other hand, if we consider the following, then you can immediately see that these two sides does not transform in a similar fashion under a general coordinate transform. So if you go from some x to x prime under some GCD, so the left hand side will transform that x mu prime nu, A prime nu, and the right side will transform nu B, some B prime nu. So you can see if you go to some prime frame, this equation, or rather the form of the equation does not remain same. You will have the Jacobian or the inverse Jacobian matrices depending on where the initial indices. It just follows from the usual tensor transformation rules that we discussed previously. So the first example is example of covariance, and the second example is this is not covariant. It changed, the form change. But if you now consider this equation after this transformation, and you can do another GCD, let's say from x prime to say let's x double prime, then you know that how this A prime will change and B prime will change to some A double prime and B double prime, and then this equation will become the following: del x mu del x double prime nu equal to del x double prime nu del x mu and then B double prime nu. Okay, so now you can see that this equation is actually a form invariant under GCD. Not this one, but this equation. Because if you take this and go to some x double prime frame from x prime frame, and you notice carefully, only what happens is here the prime is replaced by the double prime. So let's compare this with the following. So write it again. Now we compare them. Okay. Now if you can see that indeed this equation is form invariant. So what it teaches us that one can always make an equation covariant under GCD. So even if you start with this equation, which is not covariant, you can make it covariant by suitable modification. In this case, you have to bring into these factors, and then the resulting equation will be covariant. So we can make any equation form invariant. And we have done that. We have covariantized various laws, electrodynamics, Newton's law of gravitation, and so on. Those are actually a particular example of these, where this is covariant with respect to the Lorentz transformation. It's a particular example of arbitrary. Okay. Now, this covariantization simply says that if you observe physical phenomena, it should be same regardless of which reference frame or coordinate you use to describe or see that physical phenomenon. Suppose you are throwing a projectile and it is getting hit, and these two things will always remain same regardless of you are observing this in an inertial frame or a non-inertial frame. So covariance principle is simply the mathematical statement of this. Right? So principle of covariance does not put any restriction to the content of the equation despite some physical laws or some phenomena, but rather it put a restriction on the form of the equation. And we'll see that that is why it has nothing to do with the gravity. We have to put some restriction on the content of the equation describing gravity. Now let's discuss what is the invariance under GCT. So invariance under GCT is much more restricted than covariance. It says that all the constants, which can be the numerical factors like u2, pi, etc., as well as some universal constant, h bar, c, etc., as well as some absolute constants, which does not get affected by the presence of our matter and energy density of the universe, should remain same under general coordinate transform. So when we mean absolute constant, we mean that those constants are not affected by in presence of our matter distribution. For example, let's say for universe. For example, absolute constants are those like speed of light in vacuum, Planck constant. In fact, these Jacobian metrics under GCT, these are absolute constants. They should not change under general coordinate. So it gives something called absolute constant. For example, speed of light in vacuum, c, h bar, the Jacobian, which is like, and of course there will be some dynamical quantities which will change it under general coordinate transformation. That is typically case of gravity, they will be affected by the matter energy distribution of our universe, like position, momentum, various fields, and so on. And then the laws or the dynamical equations should be covariant under the general coordinate transformations, and all these absolute constants that will be inside this equation should remain invariant under GCT. So let's write it down. So statement is that under GCT, the invariance means covariant or form invariant under GCT. And the absolute constants or absolute quantities appearing in these laws would be invariant under this. Together, these two, we have the invariance principle under general coordinate transform. So again, let's take a look at our previous example. So the first example we take is the following. Again, let's rewrite this equation. Mu right mu b prime. So if you take a look at this equation now, so this is covariant under GC because these forms remain same when we go from x prime to x double prime, but it is not invariant. Why? Because the absolute quantities, that is these Jacobian, are getting changed from, for example, this from del x of del x prime to del x double prime. Replaced. Now we can see that under the general coordinate transformation, which also follows from our previous discussion, that the metric, that is the arbitrary metric, is not an invariant quantity. It actually transforms. So we know that the physical distance between two space-time points cannot change under an arbitrary relabeling of this point. So dA squared, the squared line element between two points infinitesimally separated, invariant under the GCT. And dA squared is basically the absolute quantity. But the metric G mu nu is not absolute quantity. It actually transforms. So remember that sum x to x prime, we have G mu nu x mu is equal to nu sum prime x prime mu, because ds square both sides is same, and this follows from that. And from here we can write down the following transformation rule, that G mu nu at x should go to some G prime mu at x prime, and that is related to the old G mu nu using this transformation rule. Unlike the Minkowski metric, any arbitrary metric does not remain invariant under GCT. And then we can actually draw a very important conclusion that this space-time metric cannot be an absolute constant. it is a dynamical quantity when dealing with theories of gravity, which should be invariant under the general coordinate transformation. But metric is a dynamical object, and we will see that the matter or energy distribution of the universe actually affect the space-time metric. So the important conclusion is that metric is a dynamical quantity. In fact, in general, it is true for any theory which is invariant under general coordinate transformation, the metric will be a dynamical object for such theory. And this lays the foundation for our subsequent discussion, where we will develop formalism to study the nonlinear theory of gravity, dynamics of which will be described by some Einstein field equation. And we will see that given appropriate trace energy momentum tensor, the source of the mass and energy of our universe, of a system, we can solve for the metric, which is basically has to be dynamically solved, solving some equation. So we'll end here, and thank you for listening.